Good afternoon. Let us start our lecture today. So last time we were discussing how to solve this equation, right? And this is satisfied for all of the x in 0, 0, 1. So given f, you have to find u such that minus u second plus u is equal to f, and then you want to have also the boundary condition. They're both 0. All right. So in this case, you see that if there is no coefficient ux, then the problem becomes very easy. But because of the appearance of this ux, things become complicated, and you have to use all of the complicated tools that you know from functional analysis. So the tool that we used was the Laxman theorem, because you're gonna turn. So you wanna find a weak solution in S01, 01, such that u prime v prime dx 01 plus ux uv dx is equal to 0 fv dx for all of the v in S01, right? So we're gonna have to find which solution in the sense that it satisfies this identity for all of the v in S01. So according to Laxman, we know that, okay, we know that there's a unique solution such that it satisfies this equation. So no. Yes. Okay. So we showed that there's a unique use such that this is satisfied, and then to find u, we use finite element method, right? So the idea of finite element method is to construct a finite dimensional space h small h, which is an approximation. Right? So the idea is to find a finite dimensional space such that this HS approximate the bigger space H01 and solve integral from 0 to 1 of u prime h v prime dx plus uv is equals to integral from 0 to 1 of fv dx for all of the v in the small space. So for UH in this small dimensional space, right? So the idea of finite element method is to construct a finite dimensional space HS, which is an approximation of the space S01. And when you solve this problem on the finite dimensional space, you want to find UH in this finite dimensional space such that the same relation holds, but only for all of the v in this finite dimensional space. So how to construct HH? So the idea is simple, right? So the idea is that, okay, you divide interval 0 to 1, and this is x1, x2. So this is x0, x3, xn, and this is xn plus 1. All right, so you divide this interval into smaller intervals with the same size. And then, for instance, if you have a function u, so this is the function u. And so the idea is similar to what you see in the Riemann Riemann intervals, right? You're gonna approximate you approximate this function u by piecewise linear function, right? So you gonna approximate by piecewise linear function. Piecewise linear function. And this is h, right? So for a function u in h, what you do is that, okay, you draw this function from 0 to 1, right? And then you divide 0 to 1 into smaller equal intervals. And then you approximate this, this curve by piecewise linear functions in h small h. And this is how you construct some h small h, right? So h small h will be piecewise linear function u on x0 to x1, x1 to x2, xn plus 1 to xn, right? So the space hs will be the space of piecewise linear function. So you have x0, x1, x2, x3, x4, xn plus 1. So this is 0 and this is 1. So what you do is that you approximate this by piecewise linear function. And this is basically the space the space hs that you have, right? So this is, suppose that you have a function like this, then you're going to approximate that by some linear function. So you approximate the curve by straight line. All right. So, but of course, those function has to satisfy the condition that, okay, it has to be 0 here. So there was a mistake in the picture. So basically, you're gonna have to satisfy the condition that u at 0 is 0 and u at 1 is 0, right? So the idea of this finite dimensional space will be the collection of piecewise linear function u that connects all of the points on this interval, and the length of each interval will be h. And what we do is we're gonna send h to 0. We send h to 0. All right. So when you send h to 0, you're gonna have the more and more accurate approximation of the function by piecewise linear functions, right? So there's one thing that I didn't show, but I guess that you can show by yourself, is that, okay, piecewise linear functions on 0, 1, S0 with 0 boundary condition. 0, 1 functions, right? So, but this is, you can try to prove that I don't want to prove that. You can accept this result, right? So the fact that I can approximate S0, 1 functions by piecewise linear function is because they belong to S0, 1, all right? Right, and then, so now one thing is that, okay, so this space of piecewise linear function will have the basis hat functions. All right. So in the previous class, we also discussed that for all of the piecewise linear function that we have here, the basis will be the hat function. All right, so the hat function will be something like this. So you have x0, x1, x2, x3, xn plus 1. So the hat function will be a function which is like this. All right, so it's gonna be 1 at one of the points x1 to xn, and it's gonna be 0 at the other points, right? So, and then this is also another hat function. Right, so basically you choose one point. For instance, I choose x3. So I choose x3. So I said that at x3 the function is not 0. So basically it's gonna be like this. All right. So so the basis for the space of piecewise linear function from 0 to 1 will be all of the hat functions. Any questions? All right, so if there's no questions, we're gonna continue. So so far what we said is the following. We said that we're gonna restrict ourselves on this space. And then this is true for all of V and VHH, and U is something that we need to find U, H in HH, right? So this is the finite element form of the original equation. Right. So the idea will be that you're gonna find a function UH in the finite dimensional space UHH such that B UHV will be equal to LV. Sorry, LV for all of V in VH, and this is the goal that the function that you have to find. Right. So now I'm gonna write UH as the sum when n is going from 1 to infinity of Cn Vn, right? Because no, so n from 1 to n, because we have n so n basis, right? So this is the hat function. And we need to find Cn. Right? So I explain again. You want to find a function UH in HS such that B UHV is equal to LV for all of the V in HS, right? So this is basically the finite element form of the original equation, and this is the simplest example of finite element method that I'm showing you, right? So in this case, you have an elliptic equation which is in 1D, and you have to solve this equation. So the idea is that okay, you're gonna write UH on the basis of Pn. So you have n, capital N hat functions that form a basis for h, small h. And because when you write it on this basis, you're gonna have to find Cn, right? So there n unknown. C1, C2, Cn. Right? So in this case, you have n unknowns, which has the n coefficient C1, C2, Cn. So basically, this become a finite dimensional problem, right? So this return right? So so in this case, you have to find n unknowns, which are C1, C2, Cn. And then this return to a finite dimensional problem. And now I'm gonna have to find all of these B of C1, V1 plus C2, V2 plus Cn, Vn, V, and this is equal to L of V. All right. So how can I solve this system, right? So now I have a system of n unknowns. So who knows how can I find this? How can I solve this system? No. So I have so phi1, phi2, phin, they're all of the hat functions, right? V is a piecewise linear function. I have B of C1, phi1 plus C2, phi2, Cn, phin, V is equal to L of V, right? So in this case, C1, C2, Cn, they are the unknowns. Phi1, phi2, phin, they are the hat functions which are given. V are all of the right. Surab was correct. So Surab, so in this case, Surab gave us a hint, which is to convert this into a matrix equation. So let us try to convert this into a matrix equation, right? So first, because of the linearity here, right? So Surab ideas is to use matrix equation, and then this is correct because you can write the right hand side in the form of C1 B of phi1 V plus C2 phi B of phi2 V plus Cn B of phin V is equal to LV, right? So now how can I turn this into a matrix? Right? So using matrix is an excellent idea of Surab, because you can see that here you're gonna have to find C1, C2, Cn, and then you have in hand all of the functions phi1 to phin and all of the function V, right? So because of the linearity of V, I'm gonna split this guy into C1 B phi1 V plus C2 B phi2 V plus Cn B phin V, right? And this is equal to LV. But now I want a matrix equation, and how can I get a matrix equation? The idea is very simple, because this is true for all of the V. All right. So what happens if I choose V to be phi1? Right. So if I choose V to be phi1, then I have B phi1 plus C2 phi2 phi1 plus Cn B phin phi1, right? L phi1, right? So this is given, right? So because this equation is true for all of V and VH, I can replace V by phi1. So when V is phi1, I have C1 B phi1 phi1. When V is phi1, I have C2 B phi2 phi1. When V is phi1, I have Cn V B phin phi1, and this is equal to L phi1, right? So this is given, right? So basically, this is what this I call this C1 times. So this is a constant. I call it B11. C2 B21 plus Cn Bn1, and L of 1 is given. So this is going to be A1, right? So then this becomes something simple, right? C1, this is a constant which is given. C2, this is a constant which is given. Cn times Bn1, which is a constant given, given constant. And then you have A1, which is also a constant. I have one equation, but I want n minus one more equation to get a matrix system. How can I get the other one? So I can keep replacing, right? So I can keep replacing V by V2. So when I replace V by V2, I'm gonna get B V1, V2. Then here I have C2, B, V2, V1, V2. And here I have Cn, B, Vn, V2. And then this is L of V2, right? So this is again given. So I have B12, C1, plus C2, B22, and here I have Cn, Bn2, and this is A2, right? So then I have another equation, right? Again, I explain again. So here I have to find the coefficient C1, C2, Cn, such that C1b V1v plus C2b V2v plus Cnb Vnv, and this is equal to LV. This is true for all of the V in HS. What I do is I gonna make a matrix equation out of this system. So what I do is first I replace V1, V by V1, then I have C1b V1 V1 plus C2b V2 V1 plus Cnb Vn V1, and this is equal to L V1, right? So because V1 V1 that are both given, the form of B is given because this is the U prime V prime interval plus UV interval, right? So when I give you those functions, you can compute B V1 V1. You're gonna have C1 B11, then this guy will give you C2 B21, and this guy gives you CNB N1, right? So, and then you keep doing the same thing. You replace V2 there, you're gonna get C1 B12, which comes from B V1 V2, and then C2 B V2 V2, which comes from B22, and then you're gonna get B Vn V2, which gives you Bn2, Cn Bn2 is equal to A2, and at the end of the day, you continue this process, and then you're gonna get the following equation. You have C1 C2 Cn, right? And then you have B11, B21, Bn1, and then you have B12, B22, Bn2, right? And then you have B1n, B2n, and then you have Bnn, and everything will be A1, A2 again. So I think I have to put this onto the other side. C1, Cn, right? So the idea will be, so after you do that, you're gonna have B1, you're gonna have a matrix B, which is B11, B21, Bn1, B12, B22, Bn2, B1n, B2n, Bnn times C1 to Cn is equal to A1 to An. All right. So and then Bij will be the B of Vi Vj, and then Ai will be L of Vi. And then you inverse this matrix, and you can solve the equation, right? So basically, you're gonna have a matrix B times C1 to Cn, and this is equal to a matrix A, and then this becomes a matrix equation, right? And then when you solve this, you can find C1 Cn, meaning that we can find UH, which is C1 V1 plus Cn Vn. All right. It's clear? So the idea is the following. The idea is that because this system is true for all of the V, you can replace the V by, for instance, V2. When you replace V2 there, you're gonna get what? You get C1, B, V1, V2, which gives you B12, C2, B, V2, V2, which gives you B22. And then this is Vn, V2, which gives you Bn2, right? So when you put things together, you're gonna have n unknowns, but you're gonna have n square coefficients. This gives you a matrix of the type B11, B21, Bn1, B12, B22, Bn2, B1n, B2n, Bnn times C1 to Cn. So the right hand side will be A1 to An. Those are constants that are given. So now it becomes a simple matrix equation. You can solve it by anything that you want. So when you do that, you're gonna have the coefficient C1 to Cn. Once you have the coefficient C1 to Cn, you can find UH, which is C1 V1 plus Cn Pn, right? And this is how you solve it by finite element method, right? So this is the most basic example, the most basics example of finite element method. Any questions? Right. So now because our class is analysis and functional analysis, so we are not going to the implement of this algorithm, but in order to understand this method, we have to understand what is the theoretical support of this idea, right? So questions that we want to answer. So suppose that you have B UH V is equal to LV for all of the V in HH. So H will be the mesh size, all right? So what we want is that we want that as the mesh size H goes to 0, UH converts to U, which solve BUV is equal to LV, right? So I explain again. So because this is the equation that we want to solve. We want to find a solution U of the original elliptic equation, BUV is equal to LV for all of the V in H, right? Our idea is to create a finite dimensional space HS by piecewise linear function. And you solve this problem on the space of piecewise linear function. Now, can we do that? I mean, the point is that what happens if you send the mesh size to 0? If you are able to send the mesh size to 0, and when the mesh size goes to 0, the solution that you find in the finite dimensional settling converges to the solution of the elliptic equation. Then this is the good thing to do, right? Otherwise, it doesn't make any sense. Any questions? It's clear, right? So this is why we want to understand the theoretical reason behind all of the algorithm that you use, right? Right. So the next step, we're gonna study something called a priori estimate, a priori error estimate, and a priori error estimate. right? So now so now what we want is an error estimate, a priori error estimate for the fact that you go from the finite dimensional setting to the infinite dimensional setting. So that you can pass the limit from the piecewise linear case to the continuum case, right? Right. So now we want to control the error E, which is equal to U minus UH, right? Right. So now we want to control this error, and what we want to do is that we want to show that this is of order CH. So this is the nomination. This is our goal, right? So because this is an elliptic equation, we have a priori error estimate which says that the distance between the approximate solution, which is the piecewise linear solution, and the full solution, this distance is of the edge, which means that if you let this edge go to 0, the solution, the approximate solution, will go to the original solution, right? Any questions? So first, let us consider this BE, right? So what is the lower bound for BE? So E will be this error, UH minus U, right? So the first thing that I want to know is what is the lower bound of BE? What is the property of the bilinear operator B that we can use to have a lower bound for BE? No? What is it? Yes, so Abdullah is correct. So you have the coexivity, right? So according to Abdullah. Right, so we know that, okay, BE is bounded from below by alpha E square. So this is the so-called coexivity, right? Which means that if I can bound from above, so meaning that if we can bound above by E times H, for instance, then you're gonna have EH smaller than EH, leading to EH is smaller than CH, right? So according to Abdullah, this B is a bilinear form, meaning that BE is bigger than or equal to alpha EH square, right? So this means that if you can bound BE from above by, for instance, EH times small h, then you deduce that EH is smaller than constant times h, and this is the error, the a priori error estimate that we can have. All right. Now let us try to bound. Let us try to bound BE. All right. So BE, I'm gonna write under the form of BE U minus UH, right? So the first thing that I can observe is that E is U minus UH. All right. So BE will be BE U minus UH. Now I'm gonna define. We define. So since HH is a subspace of H, right? U will be, U can be decomposed as U is equal to U prime plus U second, with U prime in UH, U prime second is in H minus UH, and U prime is orthogonal to UH in the sense that the inner product of U prime, U second is 0. Right? So there is one thing that I can observe, which is the following. Because this HS is a subspace of this space H, the U can be decomposed as U prime, which is in HS, and U second, which is in the space H minus the space HS, in which U prime and U second, they are orthogonal, right? Is it clear? So in this case, we define U prime to be pi of U, which is the projection of U onto HS. Right? I explain again. So you know that this B, so we want to control the error, which is the difference between U and UH. All right? So we know that B is going to be bigger than alpha times the norm of E square according to Abdullah, and this is the coercivity of the operator B. This means that if you can bound the B from above by E times the constant H, then you're gonna have immediately alpha times E squared is smaller than E times H, which means that E is smaller than H. Meaning that when you send H to 0, you're gonna, this error is going to be 0. This is what we want. All right. So now our goal is to bound the BE. So by definition, the E will be U minus UH. All right. So now because HS is a subspace of H, the U can be decomposed as U prime plus U second, in which U prime is in the space HS and U second is in the difference between H and HH. So these two components has to be orthogonal, right? So this is standard because you have UH here and you have H here. So you decompose one part is here and one part is here, and the two vectors has to be orthogonal because we are in a Hilbert space. Now this U prime, I call it the projection of U onto this finite dimensional space HH. All right, good. Now I'm gonna use this U prime into here, right? So we're gonna have BE will be BE U minus UH, and this is equal to BE U minus pi U plus pi U minus UH. All right. So I'm gonna use this projection of U onto the finite space HH. We have B of, so we have U minus UH will be U minus pi U plus pi U minus UH. So this is linear. So I have B E U minus pi U plus B E pi U minus UH. All right, because of linearity. I explain again. I define pi U to be the projection of U onto the finite dimensional space HS. Then BE U minus UH will be BE U minus pi U plus pi U minus UH. So this gives you BE U minus pi U, and then this is also BE pi U minus UH, right? So Then I'm gonna get BEE will be BEU minus pi U plus BE pi U minus UH. All right. Explain again. You get what? You get BE will be BE minus pi U plus BE pi U minus UH. Right? Good. So now I'm gonna say that the second pi is going to be 0. Why? Why? So this is quite. So it is quite easy to see that when I split BEE as BEU minus pi U plus BE pi U minus UH, then I'm gonna see that this second term will be 0. Why is it? So what is this second term? This second term will be B up. So this A will be U minus UH. Pi U minus UH is going to be 0, right? So this is the definition of the error. Error will be the difference between U and UH. So we want to show that the second term is 0. So I just write out E to be BU minus UH, pi U minus UH. And then this is BU pi U minus UH is BU H pi U minus UH. So why this true? Right? I explain again. I'm gonna split BE into two terms, BEU minus pi U and BE pi U minus UH. All right? I am saying that the second term is 0. Why is it? Because this is equivalent to B of U minus UH, pi U minus UH is 0. So now I keep the U here and the UH on to the other side. So BU pi U minus UH is equal to B UH pi U minus UH. All right? Good. Why is it? Why they're equal? We already use linearity. So from the second step to the third step, I already use linearity. Why that's 0? So I remind you what? I remind you that PUV is going to be LV for the V in H, right? And BU V is going to be equal to LV for the V in HH. And HH is a subspace of H. So can you tell me why from these two identity I have this? Right. So now my question is the following. I have BUV is equal to LV for all of V in H, and USV is equal to LV for all of V in H, right? Right. So from these two identity, another remarks, the space HH is inside the space. This is clear, right? So from these two equalities, how can I deduce that BU pi U minus UH is going to be B of UH pi U minus UH? Any ideas? No? Again. So from this, so another hint, right? So you have what? You have BUV is equal to LV for all the V in HS, right? So from the first identity, BUV is equal to LV for all of the V in H. Because this is true for all of the V in H, it has to be true for all of the V in H small h, right? Because H small h is a subspace of big H, right? So now if you combine the two facts that BUV is equal to LV for all of the V in HH, right? Then you can say that, okay, BUV is equal to BUHV for the V in HH, right? I explain again. First, U is a solution of the full equation, which means that this is true for all the V in H. But because this is true for all the V in H, it has to be true for the V in the smaller space H small h, right? Now, the second equation solves the problem on a smaller space HS, which means that BUHV is equal to LV for all of V in HH, right? Good. So now I combine the two things. I see that this is equal to LV for all of V in HH, and this is equal to LV for all of V in HH, meaning that BUV is equal to BUHV for all the V in HH. So how can I say that BU pi U minus UH is equal to BUH pi U minus UH, right? So my questions from BUV is equal to BUHV for the V in HS. How can we get BU pi U minus UH is equal to BUH pi U minus UH? Both sides equal to that things, right? But why?
Pi U minus UH is in HH.
Right, Molly got it. So according to Molly, right? So according to Molly, this is true because pi U minus UH is in HS, right? Why? This is clear because UH is in HS, right? Because we solve the equation in this smaller space, so the solution also live in this smaller space. And then because pi U is the projection of U onto HH, right? So pi U is the projection of U onto this space. So pi U belong to HH, right? Because you pick the element in so so remember that I split U as U prime, which is pi U, and U prime is in HH, right? So because UH is in HH and pi U is in HH, so pi U minus UH is also in HH, right? And because pi U minus UH is also in H small h, this is true, right? Meaning that you can replace, we can substitute V by pi U minus UH, and you get a second identity, right? It's clear, right? So, so 7. So you're gonna have BEE is equal to BE U minus pi U plus BE pi U minus UH, right? So from the previous observation, this guy is 0. So you're gonna have BE is going to be BE U minus pi U and this is bigger than alpha u e square. All right. So I explain again. We know that B is going to be bigger than alpha e square, and then you have B is going to be Bu minus pi u plus Pe pi u minus UH. This guy is 0, according to Molly. So when you remove this guy, you're gonna have alpha e square is more than Be pi u minus pi u. So any questions? If not, we can continue this on Wednesday. All right. So see you on Wednesday. Thank you. Bye. See you. Thank you.
Thank you. Bye.
Bye. Thank you.